Okay, good morning. Let's get started. Yesterday we started learning the basics of magnetism. So we learnt that charges in motion produce magnetic field. Okay. So whether you send a current through a wire, or you send a current through a coil, or you send a current through a coil with a electromagnetic core, ferromagnetic core, you can produce magnetic field. So you can produce different amount of magnetic field depending on the strength of the current, the windings of the coil, and whether you have a ferromagnetic core with a permeability mu r. So we learned that this mu r can enhance the magnetic field produced by a certain current in a coil. Okay. So this is the first concept that we learned. Then secondly, we started learning about different materials. So I told you that in layman term there are only two types of materials. So layman calls magnetic when a material gets attracted to a magnet, and if the material does not get attracted, a layman call non-magnetic. But physicists have different classification. So the magnetic materials that get attracted to magnets belong to two types, ferro and ferri magnets. And the materials that do not strongly get attracted or repelled, which are non-magnetic, belong to three types. According to recent science, there are four types. So the fourth type I will teach you later, maybe towards the end of the class. Okay, one is diamagnetic. Diamagnetic materials are weakly repelled by magnets. So which I demonstrated by the frog floating video. And you can also experiment by having a small water beaker and try to repel with magnet. So that is one type. Then we have paramagnetic, which are weakly attracted by magnets. Then the third class is anti-ferromagnetic materials. Okay. So this is something that we learnt. Then we learned to understand what causes these properties. Okay. So why certain materials are ferro or ferrimagnetic, why some materials are anti-ferro, and so on. Okay. So to this, for explaining that, I introduced you the concept of magnetic moment. So electrons as such have two magnetic moments. One is when they are going around the nucleus, they have orbital magnetic moment. And secondly, because of the inherent quantum mechanical nature, for which I cannot give you any analogy, the electrons also have a spin magnetic moment. Okay. So we have these two properties, and I told you that in materials like iron, cobalt, nickel, when you place them in a solid state, the orbital moment is quenched, basically it is 0. No contribution. So it is the spin that will finally give rise to the atomic magnetic moments. It is not just spin, it is the uncompensated spin. So far, any questions? before I erase. Okay, if not, let me erase this. So, I started with a simple explanation based on iron atom, isolated iron atom. It has 26 electrons. So, if you start with 1s and all the way to 4s, there will be 20 electrons. Then the next 6 electrons will be filled in 3D shell. Okay. So, we have 5 upspin, 5 electrons with upspin and 1 electron with downspin. This gives rise to a net magnetic moment of 4 Bohr magneton per atom. Okay. So, this is something that we learned first. So, first concept is the atomic magnetic moment. In fact, many other elements like chromium, manganese also have around 5 Bohr magneton per atom, but they are not ferromagnetic. So, it is not enough that the atom should have atomic magnetic moment. There is also something else that comes into picture, and that determines whether a material is ferromagnetic or antiferromagnetic or ferrimagnetic, and that is called exchange coupling, exchange integral, introduced by Heisenberg. So, Heisenberg proposed that when you have a system, the energy between two spins will depend on the exchange integral J. Okay. So, if you have two spins, these two spins will be parallel if J is positive. Okay, these two spins will be anti-parallel if J is negative. Okay. So, we learned that in ferromagnetic materials J is positive. So, all the neighboring spins of ferromagnetic materials will be parallel to each other, and in antiferromagnetic materials J is negative and your neighboring spins are anti-parallel to each other. Okay. Then we also learned the third, a subsection of antiferromagnetic material, where you have two neighboring atoms with the antiparallel spins, but one of them have a larger magnetic moment than the other, which gives rise to ferrimagnetic property. Okay, so this is ferro, this is antiferro. And the third one is ferrimagnetic. So, these are called ordered magnetic materials. Okay, any questions so far? Pardon? Yeah, is energy, yes.
Energy will be always positive.
There are some cases you will have this kind of formalism, it is okay. You are only comparing, like let us say you have, there will be some cases where you will encounter this situation. Do you have any answer? Yeah, you. Yeah.
That is the quantum correction in Hamiltonian.
Mm.
potential and the kinetic energy plus magnetic energy. So negative of this magnetic energy will minimize the minimum if the exposed to the magnetic energy. So that's why the E should always be in a such a way negative total energy. Minimum.
Yeah, let us say you have some energy term where there is something else, then you have this, yeah, something I can say. Okay, so after this we moved on to learn about how do we measure magnetic properties. So, we know that ferro and ferromagnetic materials you can test just by checking whether the magnets stick to the material or not, but in the case of paramagnetic or diamagnetic antiferromagnetic material you cannot see any interaction between magnet and your material. So, people physicists use precise measurements, right. So, we rely on magnetometers like VSM, PPMS, those kind of things, where we can measure the magnetic property, particularly magnetic moment or magnetization as a function of magnetic field. Okay. So, particularly vibrating sample magnetometer relies on Faraday's law of induction, which states that if there is a time varying magnetic flux and if you have a pickup coil next to this vicinity, then the pickup coil will pick up a voltage which is proportional to the time varying magnetic flux. So, this magnetic flux comes from your sample, because you are vibrating your sample, but the pickup coil is fixed, your sample is vibrating. So, the flux produced by this sample will vary as a function of time with respect to the pickup coil. So, you will see a voltage. So, once you know the voltage, you can convert this into magnetic moment, okay, by sweeping the magnetic field by using an electromagnet. You can measure magnetization as a function of magnetic field. Okay. So, if you do this for paramagnetic materials, the magnetization will increase linearly with respect to magnetic field, and the path for going up and coming down are 0, the same. So, paramagnetic material will have positive slope, and this slope is called susceptibility. So, we can say positive susceptibility, and if you take diamagnetic material, so this MH curve will show a negative slope, and again the path is the same whether you go this way or the other way. So, diamagnetic materials have negative susceptibility. And I also told you that if you want to distinguish between paramagnet versus antiferromagnetic material, you have to measure the chi as a function of temperature. So, basically you are looking at this slope for many different temperatures. So, if your chi is going like this, exhibiting 1 over T behavior, this is an indication of paramagnetism. And for diamagnetism, the susceptibility is independent of temperature, negative, whereas in the case of antiferromagnetic material, you will see a peak, then beyond which you will see this 1 over T behavior. That means, above this temperature antiferromagnetic material is paramagnetic, and here it is antiferromagnetic. Okay. So, this temperature, this critical temperature above which it becomes paramagnetic is called Néel temperature. Okay. Any questions so far? Okay, then we moved on to discuss ferro or ferrimagnetic materials. So, in ferro or ferrimagnetic materials, let us say you want to measure the magnetization as a function of applied field. The magnetization will not increase linearly, it will go non-linearly and saturate at certain field. And when you reduce the magnetic field, it will not follow the same path, but it will follow different path, and it may retain some of the magnetization. So, in all the other cases before, whether it is diamagnetic or paramagnetic, antiferromagnetic materials, all those magnetic materials will have almost 0 magnetic moment at 0 field. Okay, only ferromagnetic materials can retain magnetization at 0 magnetic field. Okay, then if you reduce the magnetic field, change the direction, increase the magnitude, it follows a different path. Okay, if you do this again, it follows another path. Okay. So, this property is called hysteresis loop, and we learned a few concepts like saturation magnetization, remnant magnetization, coercivity, and say saturation field and so on. Okay, so, these are important parameters related to a ferromagnetic material. And ferrimagnetic materials also will have similar hysteresis loop. There was a question about how do we distinguish between ferro and ferrimagnetic materials based on hysteresis loop. I haven't answered, maybe I will answer another time. Okay. So, based on the hysteresis loop, now we can measure MS, MR, coercivity and so on. So, depending on the value of these parameters, we can classify materials, ferromagnetic materials or ferrimagnetic materials into two types, hard or soft. Okay. Hard magnetic materials usually have large remnant magnetization with respect to say MS, we can say large MR over MS. They have large coercivity, MS may be moderate, whereas soft magnetic materials usually have a large MS, but they have a small MR with respect to MS, and they have a small coercivity. So, both type are useful. So, some of for example, soft magnetic materials have their own use in transformers, in the writing heads of hard disk drive, and in electromagnets. All these applications you need soft magnetic material. Okay. Hard magnetic materials, because they can retain the magnetic polarity. So, you can use them in motor and any application where you need a permanent magnet, and you can use these materials for storage, memory. So, if you take modern automobiles, right, it is said to be that the modern automobiles have thousands of permanent magnets in different places. For example, you have say wiper, or you have steering, power steering. So many places you will find permanent magnet in an automobile. Okay, this is a huge market. China is holding a large economic value in permanent magnet. So, similarly, soft magnetic materials will have like transformer, electromagnet, and so on. Okay, so this is where we stopped. So, when we were doing this, there was a question, what is the origin of these properties? So, why some materials are hard, why some materials are soft? Okay, this we haven't discussed. Okay, so today we will start from here. Okay, so the origin for the hard or soft magnetic property of a material comes from this property called anisotropy. Okay. Okay. So, before I say anisotropy, let me discuss isotropy. Suppose you measure a physical property at different direction. Let us say this is a piece of material and you want to measure the resistivity of this material. Let us say this is a piece of copper block and you want to measure the resistivity of copper. Okay. Let us say at first you send a current in this direction, you measure the resistivity, you measure, you send current along this direction, you measure the resistivity. So, you will find the value to be the same. Okay. Resistivity of the copper is the same irrespective of the direction in which you measure the property. Okay. So, these kind of properties are called isotropic. That means, the measured property is the same when you measure in different direction. Okay. So, when we say anisotropy, it is the opposite of isotropy. Okay. So, anisotropy means the property that you measure will depend on the direction in which you measure. Okay. So, that is basically anisotropy. So, when we talk about magnetic anisotropy, we are talking about the magnetic property being different depending on the direction in which you measure. Okay. So, let us take a few cases. Let us take let us say this is a piece of magnetic material you have. Okay. So, in this material, for example, if I measure hysteresis loop along this direction or I measure hysteresis loop along in the other direction, if the hysteresis loop is different in two directions, we can say that this material has anisotropy within this plane itself. So, we are measuring the property within this plane, but only the direction is different, either along x or along the y direction, but the properties are different. Okay. So, that is what I have shown here. So, for example, in one direction you may be easily achieve saturation. Easily means with very small magnetic field you may be able to achieve saturation. So, let us say I am applying a magnetic field along the x direction. Let us say this is the x direction and I am measuring the magnetization as a function of time. Okay, let us say it goes like this. Now, I am doing the same measurement on the same sample. Now, I am applying magnetic field along the y direction, which is along the shorter length. Okay. Now, my hysteresis loop, look, let us say something like this. Okay. So, you can notice a few differences, right. Firstly, in the case of x direction, I needed a much smaller field. So, within this field I can reach saturation. So, somewhere here I can reach saturation, whereas in the case of y direction I need much more magnetic field to reach saturation. That is one thing that you see. Secondly, you look at the remanence is low in the y direction and it is high in the x direction. Okay. So, you can see a few differences in the properties. It is the same material, but only you are measuring the property in two different directions and the hysteresis loop look different. Okay. So, this property is called anisotropy. That means, the property of the material that you measure depends on the direction. So, it is a direction dependent property. So, then we call it an anisotropy. Okay. So, in some materials you can have this kind of anisotropy. That means, in one direction, I mean within the same plane. So, here I am measuring the magnetic properties of the film in the plane, okay, by applying magnetic field parallel to the plane. Okay. So, in plane itself there are two directions, one easy direction. Easy direction is the one where you can achieve saturation easily. So, the red is the easy direction and blue is the hard direction. Hard direction means you need more magnetic field to saturate, easy direction means you need less magnetic field to saturate. Okay. So, you can see the differences in the property. So, this is happening within the plane. So, we call it in plane magnetic anisotropy. Then let us take another piece of sample. Let us say another piece of sample is a different type of sample from what we have here. So, in this case let us say I apply magnetic field perpendicular to the direction. So, my magnetic field is along this direction. I am measuring hysteresis loop perpendicular to the plane of the sample. Okay. So, in the perpendicular direction, now we so perpendicular direction is z, right. So, in the perpendicular direction I can easily saturate the sample with a very small magnetic field and I can retain a large amount of magnetization even after I remove the field. So, we can call the z direction as the easy direction, whereas if I apply magnetic field along the x direction or y direction, I find that okay. So, remember in the when I apply magnetic field in the z direction, I can easily saturate, I can retain lot of magnetization. On the other hand, if I apply magnetic field in the x direction or y direction, I need more magnetic field and I cannot retain much of the magnetization. Okay. So, now we can say the perpendicular direction is the easy direction and the plane direction or the hard directions. Okay. So, if you have that property, for example, the the measurement along the perpendicular direction gives rise to easier saturation, larger retention of magnetization, but within the plane it is difficult to saturate the magnetic field. Then we say that this material has a perpendicular magnetic anisotropy. Okay, so people use the word, acronym PMA to represent perpendicular magnetic anisotropy. Okay. So, let us consider some analogy. Okay. I have already described what is anisotropy, but I will try to give this analogy so that you can remember it better. Okay. Let us say you have a huge plateau which has this shape. Okay, is a plane. Okay, you have a car. So, you try to drive your car along, say, x direction, y direction, any direction, you will find no difference. Okay, this is a flat area, flat terrain. So, whether you go from here to here or here to here, you will you will press the accelerator almost the same amount, let us say 2000 rpm, then you can reach the same distance in different directions when the plane is like this, okay, and the terrain is like this. Okay. So, if you have a open flat ground, driving a car in any direction will be almost identical, you will find no difference. Okay. So, we can say this is an analogy for isotropy. So, whether you drive any direction, you will find it similar. So, that is isotropy. Now, let us say you have a scenario like this. Okay. You have a road which looks like this. Okay. So, in this case, let us say you want to drive from here to here towards me. Okay. You will find it easy, okay, because it is a straight road, right. You will find it easy, no problem. On the other hand, if you have to drive along this direction, okay, you need to press the accelerator a lot. Okay. So, you will find one of the direction to be difficult. So, this is hard, this will be easy. Okay. So, here you press 1000 rpm acceleration, also you can just move, but here maybe you need 2000 rpm in the first gear and so on. You will find it hard here, easy here. Okay. So, you can say this kind of road is anisotropic. Okay. So, you find it different in different direction. So, that is the analogy for whether you can saturate with a lower field or you need very high field. Okay. So, that is one definition of easy and hard direction. The second definition is about retention. So, if you remember, I told you easy direction you retain a lot, in the hard direction you retain little magnetization. Okay. So, again that also you can understand by this analogy. Let us say you drive a car from here to here, say at this point you apply brake, okay, remove the brake, your car will be still here. Okay. Same thing. So, in this case the easy direction, let us say you drive your car from here and you apply brake, remove your brake, okay, your car will be still here. Okay. So, car will be left where you left it. On the other hand, let us say you try to drive along this one, this direction, you apply brake, remove the brake, what will happen? Yeah, the car will come back, it will not stay here, it will come back. So, this is another property of the hard direction. So, this is equivalent to retention of magnetic moment. So, here I am talking about retention of car in its initial position, but in magnetism we are talking about retention of magnetization. So, in the case of easy direction, you apply magnetic field, you have certain magnetization, and if you remove the magnetic field, you are almost there. Okay. So, you retain much of the magnetization. So, this is a property of easy direction. In the hard direction, you will almost retain nothing or a little bit. Okay. So, depending on the property of the material that you make, in the hard direction you will basically retain much less. Okay, so that also explain what I have drawn here. So, you can see in the easy direction we have retained much of the magnetization, in the hard direction we retained less. Okay. So, these are the important properties of anisotropy. Okay. So, if you measure properties of a sample in the easy direction and a hard direction, you will find these differences. For example, in the easy direction you need very small field to raise the magnetization value very quickly. Okay. Here you see you need much larger field to go to that same level. Okay. Somewhere here you need much larger field compared to here. And you can also notice that once you remove the magnetic field, so you know that here is 0 field, right. So, 0 field, a large magnetization is retained, whereas here the retention is almost 0. Okay. So, this will be the difference between the hysteresis loop in the easy direction and the hard direction. Okay. So, we learnt about what is anisotropy. Anisotropy is the property of magnetic material being different based on the directions in which you measure magnetic property. In the case of the car analogy that I gave, the anisotropy came because of the topography. So, in one case you have a flat road, in another case you have a road with some curvature. So, the topography gave rise to the anisotropy. In the case of magnetic materials, this magnetic anisotropy can come from various sources. So, it can come from the crystallographic nature of the sample. So, when the anisotropy comes from the crystallographic nature of the sample, we call it magnetocrystalline anisotropy. And if it comes because of the shape of the material, then we call it shape anisotropy. Okay, let's say you keep two different materials together. Let's say this one piece of material, this another type of material. You put them together, then there is an interface between these two materials. And if the anisotropy comes because of the interface between two different materials, then we call it interface anisotropy. And let us say you bend or stretch some film, you cause stress in the material, and if the anisotropy comes from the stress, then we call it stress anisotropy. And sometimes let us say you deposit a magnetic film. During the magnetic film deposition, you apply a certain magnetic field during the deposition, and the magnetic field can induce certain anisotropy in the film. So, that is called induced anisotropy. Okay. So, there are various types of anisotropy. The origin for magnetic anisotropy can be coming from various factors. Okay, let us first discuss magnetocrystalline anisotropy. So, as the name implies, this anisotropy comes from the crystalline property of material. Okay, so, whether we are going to study magnetic recording or magnetic random access memory, we will be dealing with cobalt often. Okay. So, in the case of cobalt, you have a hexagonal crystal structure. So, in this picture all these dots represent cobalt atoms. So, if you take a unit cell of cobalt, the cobalt atoms are arranged in hexagonal crystal structure. Okay. So, this is a hexagonal crystal structure. So, in the case of cobalt in a hexagonal crystal structure, this direction is the easy direction. Okay. So, traditionally we call this as A direction, and this is also A direction, and this direction is called C. Okay. So, the easy direction is along the C direction. So, what it means is that if you do not do anything special at ground state, the magnetic moment of all these cobalt atoms are pointing along this direction. Okay. So, when the magnetic field is 0, I mean in the ground state, all the magnetization is pointing along this direction. So, when you have a bulk cobalt, okay, you have a single crystal cobalt, then you apply a magnetic field along this direction. Okay. Let us say now we apply magnetic field along this direction and measure the magnetic property of cobalt along this direction 0 0 0 1. Then you notice that the magnetization rises rapidly. Okay. So, within a very small field, you can see that it jumps to a very large value. Okay. So, I told you that in the ground state you do not do anything, they are already along this direction, but this sample, this is experimental result, right. So, experimental results in this sample may be some of the cobalt atoms are not in this direction, there may be some difference in the sample condition imperfections. So, because of that you need certain magnetic field to reach the saturation value. Otherwise, I mean theoretically, if you do not apply any magnetic field also, all these magnetization are already pointing in this direction, you will need almost 0 field to reach this saturation. Okay. But this is an experimental result. So, there may be some imperfections, and because of that you need certain magnetic field to reach the saturation. Okay. So, you can see that this is the easy direction, means very small magnetic field you can reach high magnetization values. Okay. Now, let us try to apply magnetic field along the hard direction. So, you can say this is a hard direction, this is a hard direction. Okay. So, let us say this bottle represents the cobalt crystal. Okay, this bottle represents cobalt crystal, and the C axis, easy axis is along this direction, the height direction. C axis is along this direction. So, in this direction if you apply magnetic field you can saturate easily. Now, let us say we apply magnetic field along this direction. So, one of the radius direction of the bottle. So, our field is either along this direction or towards you, does not matter. So, we are applying magnetic field along the hard direction 1 0 1 0. Then you notice that the magnetization does not increase sharply, it increases almost linearly, slowly. Okay, then finally, at a very large magnetic field, it becomes comparable to the magnetization in the easy direction. So, what happens during this time is that, I mean at the 0 field all the magnetization is pointing up, then as you increase the magnetic field. So, let us say this is the original direction of magnetic moment of one cobalt atom. So, as you increase magnetic field, this is slowly coming to this direction, and for after very large magnetic field, the magnetic moment of cobalt turns towards this direction. Okay, so it rotates slowly from this direction towards your applied field direction. Let us say I reach here. Now, all the magnetic moments are pointing in this direction. Then I suddenly remove the magnetic field. What will happen? Yeah, so they will come back. So, suppose I reach 10,000, I suddenly remove the magnetic field, come back to 0, then all these magnetic moments will come back to the ground state. Okay. So, once I remove the magnetic field, it will come back here. Whereas, in the case of the easy direction, let us say I apply magnetic field here, I remove, they will be somewhere here. Okay. They will all be pointing in the direction. Okay, so this is magnetocrystalline anisotropy, and here this anisotropy is coming from the crystallographic structure. Okay. So, this is a explanation of what I showed you so far. So, I apply a magnetic field. So, initially the let us go back to the other one. So, I apply certain magnetic field in the opposite direction. Once that value exceeds certain field, you can see that all the magnetic moments flipped, but once I remove the magnetic field, the magnetic moment is still retained in the same direction. Okay, because there are two easy directions, either magnetization pointing in this direction or the other direction, both are easy directions. Okay. Now, if you apply magnetic field in the hard direction, as I increase, you can see that the spins rotate along the field direction, and if I reduce the magnetic field, they all go back to the ground state. Okay. Okay, so that is one type of anisotropy. The second type of anisotropy comes from the shape of the sample. Okay. So, let us say you have a bottle, you have a paper. So, you can see that the bottle and paper have different shapes. Okay. So, if you prepare some magnetic materials in a cylindrical shape or in the form of thin film, then you will have an anisotropy that comes because of the shape. Okay. So, the shape anisotropy is usually dominant in the absence of a strong okay. So, let us say there is no other form of anisotropy. Okay. So, there is no magnetocrystalline anisotropy. Okay. Then you prepare certain material into a cylindrical shape or the shape of a paper. Then because of the shape, there will be some easy direction and hard direction, and that is called shape anisotropy. Okay. How many of you have seen the horseshoe magnets? Have you seen these magnets? Okay. So, usually these magnets are popular long ago, maybe hundreds of years ago, when people did not have materials with a high anisotropy. Okay. So, at this point of time, I mean when people made this kind of horseshoe magnets, the materials used for these magnets themselves have low anisotropy. Okay. So, they did not have a strong magnetocrystalline anisotropy, okay, and they used this shape to create some anisotropy. Okay. So, the horseshoe magnet is one example of a magnet that uses shape anisotropy. Okay, so, to understand shape anisotropy, let us follow this rule of thumb. Okay. So, for example, let us say I have this a magnet which looks like this bottle. I magnetize along this direction. So, let us say we have a north pole here and south pole here. Okay. So, when I magnetize this magnet along this direction, you can see the north pole is here, south pole is here, and they are separated by about 20 centimeter. Okay. Now, I take the same piece of magnet, I try to magnetize along this direction, the radius direction. So, let us say I have north pole here, south pole here, they are separated by around say 6 centimeter. Okay. So, the shape anisotropy prefers that the north and south poles must be far from each other. Okay. So, we magnetize this in two direction. In one case we magnetize along this direction, in another case we magnetize along this direction. So, here you see the spacing is 20 centimeter, here the spacing is 6 centimeter. Okay. So, shape anisotropy dictates that this will be the easy direction, okay, because in this direction if you magnetize, the north and south poles are far away, whereas in this direction the north and south poles are not far, only 6 centimeter. So, this will be the easy direction, this will be hard direction. Okay, now, I have a magnet looks like this. So, here which is the hard direction? Yeah. So, this will be the hard direction, because if you magnetize along this direction, your north pole and south pole are like 5 millimeter away. On the other hand, if you magnetize along this direction, maybe it is like 30 centimeter, this direction around 20 centimeter. So, this will be the easiest direction is along this. This is a bit hard direction and this is the hardest direction. Okay. So, in a sheet of paper, hard direction is perpendicular to the plane of the paper, and if you take a long wire, the easy direction is along the length of the wire. So, if you take an ellipse, for example, so if you magnetize along this direction, the north and south poles are far away. So, this is the easy direction. If you magnetize along this direction, north and south are closer. So, this is hard direction. Okay, so, this is the concept of shape anisotropy.
Sir, what a horseshoe magnet, how will it be?
Horseshoe magnet is like your, this is the length, right. So, the easy direction is along this line. So, it is like a long wire. So, it is like this. So, it is like a long wire. So, easy direction is along this length and you just bend it. Yeah. In a single crystal and polycrystalline sample, how will the direction of field depend? I mean, in a single crystal, you can mark, like, let us say you buy a single crystal sample and it comes with a marking. Let us say they will have, this is one particular direction, and let us say this is the easy direction. You can easily measure the hysteresis loop along the marked direction and say 90 degree away from that. Okay. So, in single crystal it is easy to do. You know where is the easy direction, which is the hard direction, but in polycrystalline materials you do not know exactly, okay, because you may have texture or you may not have texture. Okay. Let me come back to this one. Okay, one example of a polycrystalline material. Anyway, to go to the white screen from here. Okay, let me draw something here. The hard disk media, the magnetic films that store information in the hard disk drive, they are a good examples of polycrystalline systems. Okay, so in this system, we have tiny crystals separated from each other, and in the recent hard disk drives, so these grains have magnetic anisotropy in the perpendicular direction. So, their magnetization may either point into the board or the magnetization may be point away from the board. And these are usually highly textured films. So, when I say textured films, we prepare the easy direction of these grains. So, now I am looking at the cross sectional point of view. Their easy direction may be mostly pointing in the perpendicular direction, whereas some grains may have slight tilting. Okay, so, this property you will see in polycrystalline materials, but in single crystalline material almost all the grains will be pointing in the same direction. Okay, so, because of that you will see difference in the hysteresis loops. So, in one case, for example, when you measure a single crystal film, you may have like very clear idea of easy direction and hard direction. But in the case of polycrystalline materials, you have like there is some variation in the easy direction. So, your hysteresis loop will be a mix of property from different grains. Okay. I do not know whether I answered your question, but you will see differences in the measurement. Okay. What is the next question?
Also, if you measure resistivity in presence of different fields,
Mm-hmm.
will the resistivity be affected by the applying different field if the material shows the photophenomenon?
Yeah. So, we will be discussing this property where the resistance depends on the magnetic field in a later section. So, we will discuss that then.
So, the last question, the animation shows for the field removal in the single crystal of cobalt
Mm.
was for a perfect crystal without defects.
Mm-hmm.
Therefore, the magnetization traced back initial path with zero remnants, right?
Animation for shown for field reversal in single crystal. In the hard direction, yes, the remnants will be 0. Yes. So, I think this question is referring to the video I showed for hard direction. So, that is anyway animation. So, I am just explaining what is happening in the cobalt unit cell level. Yes. So, yeah, you are right. Any other question? Okay, if not, let us move on. Okay, so, the shape anisotropy comes from this property called demagnetizing field. Okay. So, to understand this concept, I need to introduce a few more terms. Okay. So far I introduced magnetization, I introduced a magnetic field, applied magnetic field, but a few other things I have introduced. Okay. Let us say you have a piece of magnetic material, you apply certain magnetic field, then you can orient the magnetic moments of this particular material along certain direction. So, we can say the magnetization of this material is pointing along this direction. Okay. So, this is magnetization, and this magnet itself will produce a magnetic field. Okay. So, this magnetic field will be like this, shown by the blue arrows outside the magnet. Okay. Outside the magnet, I mean, by convention we always say that the magnetic field goes from north pole to the south pole. Okay. So, outside the magnetic field will go along this line. Inside the magnetic field will go this way, again north to south through the material. So, if I have a magnet like this, so there is a field inside this material that goes from this side to the outside through the, let us say, through the center of this bottle. Okay. So, this field is called demagnetizing field. Okay. Then you also know that by Maxwell's law, the B is always forming a loop. So, the B inside B is magnetics induction. Okay. So, it follows this pattern. Okay. So, the B, H and M of a magnet will have this kind of properties. Okay. Now, you see that there is a magnetization which is pointing along this direction, and inside there is a magnetic field that is opposite to the magnetization. Okay. So, you can notice that this H is opposite to M. Okay. So, this H will always tend to destabilize M. If H is large, then M is not stable along that direction. Okay. So, this is the reason we have the rule of thumb that I stated before. So, north and south poles must be far away from each other. Okay. So, if north and south poles are far away from each other, this field will be small. Okay. This is called a demagnetizing field. It is d small when north and south poles are far away. Let us say I magnetize this magnet along this direction, then my demagnetizing field is along this direction. Now, north and south pole are nearer, so this field will be stronger. Okay. So, it will not favor this direction. Okay. So, this is the origin for shape anisotropy. The demagnetizing field gets larger in certain direction. So, that you can understand by looking at these tensors. Okay. So, in certain direction the demagnetization field will be larger, and that will oppose magnetization to be in that direction. Okay, that is about shape anisotropy. Okay. So, here I am showing different example. So, if you take a piece of paper like this, then when you try to apply magnetic field along this direction, since the demagnetizing field is very large along this direction, magnetization usually do not stay in the perpendicular direction. And like, let us say, I mean, this example is very useful when you look at thin films. When you prepare thin films without any special anisotropy, So, if your thin film have no special anisotropy, then the magnetization will never be along this direction. Okay. The Dmag field is very strong along this direction. So, when there is no special anisotropy, the magnetization of thin film is always parallel to the film, either along this direction or this direction. Okay. So, in the case of thin films with no anisotropy, the magnetization will be either parallel along this direction or this direction. Okay. So, when you have a magnet of this shape, again when you talk about this direction, the north and south pole are very far. So, H d is negligible, but if you talk about this direction, H d is high. So, the magnetization is not favored along this direction. Yeah. So, here is a weak demagnetic field. If magnetization is along this direction, Dmag field is weak, but if magnetization is along this direction, there is a strong demagnetizing field. This is for this case. Okay, so, this is the concept of shape anisotropy. Any questions so far? Okay, now we move to the third one, interface anisotropy. So, I told you, like for example, if you make a thin film of cobalt, as such the thin film does not have much anisotropy, and because of that the magnetization is always going to be parallel to the film plane. Let us say this is a substrate, on top of this we are depositing a cobalt film. So, the magnetization will lie parallel to the plane of the film, the substrate. So, this is the normal case. On the other hand, let us say you prepare a multi-layer of cobalt and platinum. For example, this layer, the green layer is cobalt, white layer is platinum. Okay, so, you do cobalt, platinum, and so on. So, you stack many layers of cobalt and platinum one top of another for certain thickness, very low thickness. For example, let us say this cobalt is only like 0.3, 0.4 nanometer, and this platinum is like say 0.8 nanometer or so. So, when you deposit very thin layers of cobalt and platinum, stacking one top of another. So, people have found out that this film can have perpendicular anisotropy. Okay. So, here you have lots of interfaces of cobalt and platinum. So, here your cobalt is cobalt throughout. Okay. So, the cobalt atom here, cis neighbor also is cobalt, bottom neighbor, top neighbor, all are cobalt for this particular case, whereas in this case a cobalt here will see platinum as the neighbor in the top surface and so on. Okay. So, you are modifying the interface, and because of this interface there is a perpendicular magnetic anisotropy. Okay. So, now here this is the easy direction. Now, you see that the easy direction is pointing perpendicular to the film plane. So, somewhere in 1980s, people found out that when you deposit multi layers of cobalt and platinum for certain thickness, you can have the magnetization in the perpendicular direction, and this type of anisotropy is called interface anisotropy. Okay, because you are creating interfaces. Okay, so, you have cobalt interfaced with platinum, platinum interfaced with cobalt and so on, and that is why you are getting this anisotropy. Okay, so, this is one example of interface anisotropy. You can interface a ferromagnetic material with an antiferromagnetic material. So, this is another type of interface. Then you can get another type of anisotropy. You can interface soft magnetic material with hard magnetic material, or you can, I mean, like I described now just now. Here we are interfacing magnetic material with a non-magnetic material, and we get perpendicular anisotropy. Okay. So, these are some examples of interface anisotropy. Okay, so, now let me explain this one, the ferro antiferromagnetic interface. Let us say you have a ferromagnetic film in proximity with an antiferromagnetic film, and this is the interface. Okay, you do some process. Okay, there is some recipe which I will give you another time. There is some recipe you need to follow, and you make this kind of film. Okay, after doing this recipe, you have the spin structures as shown in this picture. Okay. So, the antiferromagnetic spins, you can see that they are antiparallel. Okay. But at the interface you can see that these spins of the antiferromagnetic material and the ferromagnetic material are parallel. So, you have formed this kind of interface, and now if you measure the hysteresis loop of this ferromagnetic film, I mean you are measuring the hysteresis loop of this whole thing, but antiferromagnetic material will not show anything significant, because you know that their net magnetization is 0. So, what you will see is the magnetization response of the ferromagnetic film affected by this antiferromagnetic film. Okay. So, you will get a hysteresis loop which looks like this. So, this is the hysteresis loop of antiferromagnetic ferromagnetic interface. Okay, so far I have drawn many hysteresis loops, right, and here you see another hysteresis loop. Do you see any difference? Yes. Okay. You see that the hysteresis loop is shifted. So, whenever I was drawing hysteresis loop, that is symmetric with respect to the magnetic field. Okay. So far all my discussions I showed you hysteresis loop which was symmetric with respect to the 0 axis of magnetic field, but here you see that the hysteresis loop is shifted. So, this is the center of the hysteresis loop, and this is the H is equal to 0 axis. Okay, so, this is negative H, this is positive H, 0 is here. Okay, so, you see that the center of the hysteresis loop has shifted by certain field. Okay, so, this field people use different terms. So, some people use it HEX or HEB. Okay, let us use this term EB, HEB, where EB stands for exchange bias. Bias means what? Bias, you know, right? You are not in the center, you are not taking neutral decision, you are biased to one side. Okay. So, in this case the hysteresis loop is biased to one side. Okay. So, the center of the hysteresis loop is on one side of the field direction. Okay. So, it is not here, you see it is unbiased. The hysteresis loop is symmetric with respect to 0 field, but here the hysteresis loop is shifted towards one direction, it favors this direction, it is biased toward this direction. Okay, so, this field is called exchange bias. What is the condition to get this? I told you that there is some recipe which we will discuss later. So, time being you assume that you have done something and you have this, and you are measuring the magnetic properties, then you see this one. Yeah, possible. Okay. So, I asked you the question, what difference you see? I got one answer, which is the shift. Okay, that is correct. But is that the only difference you see? What is that? Huh?
The width of the hysteresis curve is of transition from the remnants to this.
Remnants, what is?
The curve transition.
It started from positive field.
Positive. Okay. I mean, what other difference you see between this loop and this loop?
Almost like rectangle.
Huh?
It's almost like
A rectangle. Okay, that depends on how. I cannot draw a perfect rectangle. Okay, so my rectangle is like this. That's not the MR is equal to. That also you can assume that I draw badly, and that's why MR is not same as MS.
The shift can be along the direction.
Pardon?
The shift can be along the y direction.
Y direction, no. I mean, we are not talking about that. A very clear difference you should be able to see. What did you say about remnants?
Of transition from the
Straight
straight line
line to?
Short transition from positive direction.
You are talking about this sharpness. No, that is not the case. That one depends on how well I can draw. I can draw exactly the same thing. So, let us say I draw, I am not very good, but let us say I can draw. That is not the case.
Also, only providing field in one direction, not on the opposite direction, like only on
No, let us say assume that I am going from here all the way here. That is not the difference. A very important difference you should be able to see.
Non-zero magnetization at the not applied field at zero applied field.
Non-zero magnetization.
When no external field is applied,
Mhm.
H0,
Mm-hmm.
it's only in the negative direction.
Yeah, okay, that is the important point. Okay, so let me erase this. So, in the normal hysteresis loop, which I draw every time, how many remnant states exist? 2, right? So, if you apply magnetic field along this direction, let us say magnetization pointing up, and here magnetic field is like this, magnetization pointing down. So, you have 2 remnant states depending on, let us say you saturate along this direction, when you remove magnetic field, your magnetization is pointing in the up direction. If you apply magnetic field in the down direction, you remove, your magnetization is pointing in the down direction. Okay. That means, if you have a magnet, so you may have north pole here, south pole here, or south pole here, north pole here, depending on which field you apply. Okay. But in this case, you see, let us say I start from here, I can go all the way, come back, go back. So, I have one remnant state. If I do the same thing, let us say again I start from here, I apply, go all the way, come back, I will end up in the same state. Okay. That means, if I have something like this, my north pole is always going to be like this. Whatever I do, I apply magnetic field, very large magnetic field along this direction. If I remove, still my north pole is going to be the same. I can never make this to be a south pole. Okay. So, let us say here this particular film has only one remnant magnetization direction. Whether you apply negative field or positive field, you will always end up with this configuration. You will never have this configuration. Okay. So, this is the property that we can get with the exchange bias, and this anisotropy is also called unidirectional anisotropy. Okay. So, as I mentioned before, previously you have two directions. So, you can have this magnet to have north pole up or south pole up, depending on which direction of magnetic field you apply. On the other hand, in this configuration, my magnet will have only north pole up, irrespective of my field treatment. Okay. So, there is only one direction. Magnetization will be only one direction. Magnetization at resonance. Okay. Remember this one. So, at 0 field, the magnetization has only one direction. So, this anisotropy is also called unidirectional anisotropy, and it arises from the interface between the antiferromagnetic material and the ferromagnetic material. Okay, we will do a few questions, then take a break. It's same as yesterday. So, if you had already opened the tab, you can use the same one. This one we have done before. Okay, we will do this. What is showing?
It's showing some code.
Some. Okay, this is a different code, is it? Yeah, same code, the one you used yesterday. So, I will give you more time for this question. So, in your browser type ooclap.com, and when it asks for code, you type spin week 2. Okay, most of you are right. The correct answer is hard magnetic materials are difficult to demagnetize. Next one. Okay, majority of you are wrong. Okay, why wrong? I cannot write here. Okay. Okay, majority of you are wrong because all of the above means this is right, but this is wrong. Okay. If you take a material, okay, let us say this material, whether you are, let us assume you are comparing between this direction and any axis within the plane. Okay. So, in the when you apply magnetic field in the plane of that paper, you will reach saturation quickly and you will have a hysteresis loop like this. Okay. Now, I apply magnetic field in the perpendicular direction. I need more magnetic field. Okay, my hysteresis loop may be something like this, okay, in the hard direction. Okay. So, at a large field what happens? At this field the MS is the same. Okay. So, whether you apply magnetic field in the easy direction or hard direction, MS is the same. Okay, by definition your magnetization is the sum of magnetic moments of all the atoms divided by volume, right. So, inside that material volume did not change, MA did not change. Okay. What has changed is only like the field you need to make all the magnetization to point in one particular direction. Okay. So, at very large field the hard direction also will have the same saturation magnetization. Okay. So, because you thought this is correct, so many of you chose this one. So, this is the correct answer. I am also wrong. Correct answer is 2. Okay. Next one. Okay, I don't know why still some of you are answering wrongly. This should be a very simple question. So, the correct answer is direction A. Okay, so we have some more questions pending. I think time to go for break. Yeah. So, we will have tea break now, then come back after 15 minutes.